So far, we have observed that light has a dual nature, which means that light have particle as well as wave nature. So the particle nature of light can be explained by three different reasons, out of which two of them, that is the blackbody radiation and the photoelectric effect, have already been discussed. In this video, we will be discussing the third reason, that is the atomic spectra. Here, we will learn about how the atomic spectra is produced, what does it say about the structure of an atom, and how it describes the particle nature of light. So, if you haven't subscribed our channel, do subscribe our channel and also like our video. So to understand about the atomic spectra, we must know the basic concept of light, as an atomic spectra is produced by the interaction of light and matter. Before, when we tried to understand about light, we saw that light is an electromagnetic radiation, and the electromagnetic spectrum obtained from this radiation consists of a region which was known as the visible region or the white light. So the white light is that continuous part of the whole electromagnetic spectrum which lies within the wavelength range of 400 nanometer to 700 nanometer. But how do we know that the white light or the visible spectrum lies in that region? So when a white light is passed through a glass prism, the white light gets split up into lights of wavelengths having different colors. For instance, we get violet, indigo, blue, green, yellow, orange, and red. Thus, we can say that the white light comprises of the wavelength range of the 7 colors. If we pass these different colors in the reverse direction through the glass prism, we get back the white light. Thus, we can say that the white light comprises of the wavelength range of the 7 colors, with the lowest wavelength of 400 nanometer and highest wavelength of 700 nanometer. So this tells us that white light is a continuous spectra lying between the wavelength range of 400 nanometer to 700 nanometer. As we have already said that an atomic spectra is produced when light interacts with matter. So when a light, especially white light, interacts with matter, that may be an atom or a molecule or ions, a radiation is emitted, and that radiation is this atomic spectra. So the atomic spectra that we are going to learn are of two types. One is the absorption spectra and the other is the emission spectra. Now we will see about these two spectra in details and how these two spectra are different from one another. The first type of spectra that we are going to learn today is the absorption spectra. So absorption spectra, as the name suggests, is obtained when atoms or molecules of a matter interact with the white light and some of the wavelengths of the white lights are absorbed by the matter. So when a white light, which is a continuous spectra lying between 400 to 700 nanometer, interacts with matter, the matter absorbs some of the wavelengths of the white light. So the spectrum have some of the wavelengths missing, and that spectrum is known as the absorption spectrum. Thus the absorption spectra looks like a continuous spectra with some dark spots which corresponds to the wavelengths absorbed by the matter. So the second type of atomic spectra is the emission spectrum. The main difference between the absorption spectra and the emission spectra is that Emission spectra is obtained only when the atom is in excited state. So excited state here means that the atom is in the energy level above the normal level. We can excite an atom either by increasing the temperature through heating or by incident of light. Whenever an atom is in excited state, the atom is not stable. For an atom to be stable, it must reduce their energy by emitting radiation, and this radiation emitted by the excited atom is known as the emission spectra. The emission spectra for different atom is different from the absorption spectra. In absorption spectra, there is a continuous spectrum with some missing lines, but in case of emission spectra, there is only few visible lines and the rest of it is dark. So this is the main difference between the absorption spectra and the emission spectra. So from this we will see what this atomic spectra tells us about an atom. To ensure that we have understood the atomic spectra of the atoms, let us consider an example. Let us take the atomic spectra of helium. If we see the absorption spectra of helium, it is a continuous spectrum with some missing lines which corresponds to the wavelength absorbed by the matter. And if we see the emission spectra of the helium atom, we saw that there are few visible lines while majority of the spectrum is dark. An interesting point to note between the two spectrum is that the missing line, which corresponds to the wavelengths in the absorption spectra, are found in the emission spectra. Thus, we can say that the wavelengths absorbed by the matter in the absorption spectra are seen as the visible lines in the emission spectra. So now let us see how we move from the atomic spectra of an atom to the structure of an atom. So the first development in this move was the atomic spectra of the hydrogen. Hydrogen was the first element on which different experiments were being carried out. So on the basis of this study on the hydrogen spectrum, we came to know about the structure of an atom. So a scientist named Balmer studied on the emission spectrum of hydrogen. So Balmer made a careful analysis about the emission spectrum of the hydrogen and tried to find a common expression for the wavelength. So the lines that Balmer took follows a common expression. So the wave number of these lines follows a common expression in which this is a constant multiplied by 1 by 2 square minus 1 by n square, where n can have a value of 3, 4 and so on. So if we put a particular value of n in the equation, in the expression, we will get a wavelength which is present in the hydrogen spectrum. So we can say that an atomic emission spectrum is unique for an atom. So every atom has different emission spectra. So this fact that the atomic emission spectra is unique for every element is used to distinguish between the atoms and is very useful in chemistry. So the atomic spectra of hydrogen provides us with some information about the structure of the atom. It also gives us information about the properties of an element. As we have seen that Balmer has given an expression for some of the lines of the hydrogen spectra, for which the wave number is given by the expression 109677 centimeter inverse into 1 by 2 square minus 1 by n square. But Balmer was not able to give the expression for all the lines. So there were other scientists who gave an expression for the lines that Balmer could not give. So the first scientist was Lyman. So he gave an expression for few of the lines in which the wave number can be expressed as the same constant into 1 by 1 square minus 1 by n square, where n can have a value of 2, 3, 4 and so on. Another scientist known as Paston, he gave an expression for few another lines in which the wave number can be calculated by the expression the same constant factor into 1 by 3 square minus 1 by n square, where n can have a value of 4, 5 and so on. There was another scientist named as Brackett who gave an expression for calculating the wave number. Expression has the same constant multiplied by 1 by 4 square minus 1 by n square, where n can have a value of 5, 6 and so on. And at last, a scientist named Pfund gave an expression for the wave number, which is the same constant into 1 by 5 square minus 1 by n square, where n can have a value of 6, 7. Here, all these expressions have the same form except the initial terms are changing. So here it is 1 by 1 square. In the second one, 1 by 2 square. Here 1 by 3 square, 1 by 4 square and 1 by 5 square. So the hydrogen atom consists of various lines which corresponds to different expressions. So a scientist named Rydberg, so he gave a common expression for all those lines. He said whatever be the lines of the hydrogen spectra, the wave number of that lines can be expressed as RH into 1 by n1 square minus 1 by n2 square, where RH is the Rydberg's constant. RH is same as this constant value, that is 109677 centimeter inverse. Here n1 is less than n2. n1 can take a value of 1, 2, 3 and so on, and n2 can take a value of 2, 3, 4 and so on.